Hello everybody, we are the chaotic architectures, Rudhr, Aarez and Aadil, and today we will be presenting the Earthquake Simulator 3.0. But before the action, Aadil will explain us about earthquakes.
Now I'm going to be explaining about earthquakes and tectonic plates. So, tectonic plates usually slide past each other, but when they get stuck, due to intense friction, they might snap and slide into each other. This causes the earthquakes. Now, what is a hypocenter and epicenter? Hypocenter is where the earthquake happens but underground. It is where it begins from. And epicenter is where it happens at the surface. Now Rudhr will be explaining about the seismic waves.
Seismic waves are waves created by the earthquake which travel through a certain area depending on the magnitude. Now Aarez will explain how they are measured.
Now, I will be talking about the seismometer and the seismograph. A seismometer is an instrument used to measure the ground vibrations. This forms a seismograph, which using it can help determine the strength of an earthquake. To determine the strength of an earthquake, we use a unit of measurement called magnitude, which shows the strength of the earthquake. For example, magnitude 1 shows the least strongest, while magnitude 9 is one of the strongest ones. Now we're going to be moving on to an actual experiment.
Now I'm going to be explaining about our earthquake simulator 3.0. This is mostly made out of Legos. These two base plates resemble the tectonic plates, and this resembles the earthquake and the movement between them. We have used sponges to make a more dramatic effect for our towers. Now let's get into the action.
We have made. These towers are made up of marshmallows, big sticks, chopsticks, and also some popsicle sticks. I'm going to talk about the first three triangular towers. This one looks pretty stable and it feels stable. This one is a tall one with less connections, but they are fixed pretty strongly. This one has the more weaker connections, so there's a possibility of that falling out easily. We will have to see. First is the red one. Now we have used some toothpicks to connect the tower to the sponge to act as a foundation, which is mainly used, which is all the time actually used for the big buildings you see outside. We're actually gonna go test and see how stable it is. Oh, you can see some shaking. Overall, it's actually pretty stable. So we can redeem that this tower is one of the stable ones. This is the tall and big one. We're gonna see if this tall tower can even survive this earthquake simulator. 3, 2, 1, go. Whoa! Now, as you could have seen, the top part was actually shaking much more than the bottom. We can imply this in the real world that for tall tower, the more high you are during an earthquake, the more you will feel the vibrations. Moving on to next. Now on this tower, we're going to showcase what would happen if a big tower had weak connections. 3, 2, 1, go. It's going to fall. Yeah, so as you can see, it's really dancing just now. And I'll explain you why. Because the connections were so weak, the tower couldn't even support itself. This is showing the real world why buildings have really strong connections. Otherwise, this is going to happen like this. Now we're going to move on to the next experiment.
Now I will be showing you a triangular structure which has a strong connection and it is short. This is more stable. Now let's see what happens. As you can see, it was very stable, there was no wobble and it was perfect. Now I'll be showing you a structure made in the form of a square. Since squares are weaker than triangles, we will see exactly what's going to happen in this case. Okay, as we observe now, The structure of this tower is very weak. So what we could do to improve this is a method called cross bracing, where we attach reinforcements in between to make it into a triangle, which will make it more stable.
As you seen in the before experiment, didn't have any cross bracing, but this tube right now has cross bracing and it's reinforced with more better structures. Let's see how it works. As you can see, this is more stable than the last one as it has cross bracing. Go. As you can see here, it is a very long rectangular tower. Let's see how it goes. After the earthquake, you can see that this one had the most wobbling effect than all others. Fun fact, did you know there was a golden rule for earthquake safety? The DCH, drop, cover and hold on.
From this experiment, we learned that architecture, structure and foundations are the three key components for a stable structure, which is very important to us because it will prevent disasters like earthquakes from happening. Thank you, and this is the Chaotic Architectures signing off.